complexity of life. Thank you.
Thanks, Alex. I hope you hear me, and I hope they will hear me online if that's the way it works. So indeed, I'm a game theorist, and I like game theory. In fact, I should have shown you one thing. I'll show it to you later, maybe. I write a game theory blog also, which is called Game Theory in Everyday Life, and I think there's not enough of that, and that's why I'm doing this. So game theory can be applied whenever there is interaction. Strategic interaction is what I write here, because humans often are considered a bit more strategic, but it can actually be interaction between plants or animals, and they're also in some sense strategic, only they have not, maybe they're not very consciously strategic, but maybe they are doing this because of their genetic makeup. But anyway, so I'm going to talk a little bit about game theory in general, but I want to stay close to an example. It's what I was told is a good idea. And the example I have is a paper of mine on cognitive empathy in conflict situations with a former PhD student of mine, Florian Gauer. And this is not really in some sense economics, although I'm published in the economic journal, because game theory is developed mostly in economics, but it's now getting outside of that too. It started in math initially, but now economics really took it up a lot, and now it's, I think, a bit more broadly useful. Game theory is pretty old, started in the sort of 20s. It was really started in the 40s, and then it took off in economics in the 70s, and then from then on, but so it's still, however, underutilized in my opinion. And I think one of the reasons is that it's sometimes a bit complicated in terms of the math. Okay, so this is maybe one of the reasons why it's not an easy to use toolkit in some sense. You can't just press buttons and things will happen. You have to prove things a little bit. But nevertheless, I think it is a very useful toolkit because of its generality. Okay, so in my opinion, game theory is to building theories about strategic interaction what statistics is for data analysis. Okay, for empirical work. This is a bit bold claim, but this is how I see it a little bit. So if you want to build a theory, you should use game theory. I mean, if it's about strategic interaction of some kind or another. So let me give you the motivation for the application. And so as you saw, it was called cognitive empathy in conflict situation. So conflict situations, you can imagine what sort of things they could be. I mean, we could talk about the Ukraine, for instance, although I don't know enough about that to be saying something meaningful. But I like this old quote by Sun Tzu, The Art of War. So it's 2,500 years ago. And he wrote something like this. Let me read this to you. If you know the enemy and know yourself, you need not fear the result of 100 battles. If you know yourself but not the enemy, for every victory gained, you will also suffer a defeat. If you know neither the enemy nor yourself, you will succumb in every battle. I guess so what he was driving home is that you should be mindful about others. And that's what I would call, you should have cognitive empathy. You should try to put yourself in the other person's perspective, especially in conflict situations, and somehow think through what they will do, and then you perhaps can think about how you should react to this. However, I mean, it has a bit of a problem, right? A little bit, if you think about it. If you know neither the enemy nor yourself, you will basically lose, right? But what if your enemy is of the same kind, okay? If the enemy also doesn't know either himself or herself, or yourself or you, I mean, then, I don't know, either they both lose, I guess, which is perhaps feasible. But okay, anyway, but I don't want to say this is not right. So that I know what he was driving at, but I want to think a little bit deeply about, is it really important in conflict situations to know something about your opponent? What do you want to know? And how much do you want to know? And how much cognitive empathy should you have? So conflict situations like the one, like wars, I guess, but also others, have one thing that you want to do. You want to be unpredictable, sorry. You want to be unpredictable, right? Because, I mean, unless you have overpowering force, you can do whatever you want, okay? But if you don't have that, then you probably don't want to make predictable maneuvers that if the enemy can sort of discover and predict, so because that would be too easy for them. And I don't want to think about war, because war is so complicated and so big, but I want to think about smaller situations, okay, that you all know about. So for instance, if you think about the police trying to catch people speeding, now you know how they do this with their speed cameras. Now what they want to do, they don't want to be famous for always being in the same spot. I mean, sometimes they do, because sometimes they want to say, well, this street is very dangerous, so you want to be on that spot, so you want to make people slow down, definitely there. But they have these fixed things, right? But when they do this with their little speed cameras, they're trying to be unpredictable. They try to hide, they try to be such that you don't foresee this, so that you can catch you. Because if it was always completely foreseeable, everybody would always know where they are doing this, and you would slow down just there and nowhere else. Right? So there's no point in that. So this is also putting yourself in the shoes of a terrorist. If you want to do a terrorism attack, you don't want that to be predictable. I don't want to give advice to terrorists. I'm sure they know how to do this themselves. But you don't want to be predictable, because then they will be there ready and waiting for you to pick you up and protect them, the rest of the world. But in the same vein, if you want to prevent terrorism attacks, for instance, there's a program, in fact, initiated by a computer scientist who understands this kind of game theory. They had this program where they have air marshals that are on the plane, right? They're hidden among the passengers. They are not visible. You cannot see that these are air marshals, but quite a few planes fly with air marshals, or they used to after 9/11 especially. But they didn't have enough air marshals for all these planes, so they had to allocate them. But they didn't want to do this in a predictable manner, right? Why not? Because if you do it predictably, then, terrorists will eventually find out about this predictable pattern, and then they can avoid it. Okay, they will just go on a plane where they are sure there is no air marshal. So you want to do this again, unpredictably. The same person, actually, this computer scientist who is now in Harvard, I think, Tam Bay, I think his name was, also has these programs initiated, so algorithmic, randomizing protocols, but the randomization is the important thing. This unpredictability is where you schedule vehicle checkpoints for airport security or canine patrols for drug trafficking. Again, all these things you put in place, and you don't want to be famous for always being in the same spot, because then everybody will just avoid that spot, okay? So you always want to be unpredictable. My last thing, this is the one I'm going to use for my motivating example in a moment, where I go deeper into this, because it's the easiest of all of them to think about, is a conflict situation as a penalty kick in a soccer game. This is a very simple situation. There's one person who kicks and tries to score, and the other person in the goal is going to defend the goal. Okay, again, you don't want to be predictable. In fact, economists actually have looked at a lot of penalty kick data. There's a famous paper in 2003 in Econometrica by a guy called Palacios Huerta. And he was looking at how people do this, and they do it exactly as the theory will predict. Okay, unpredictably, however. So it's predictably unpredictable. It's predictably unpredictable. Okay, whatever that means. Okay. So, but my question today is: in all these situations, is it important to fully understand your opponent? And what does it mean to understand your opponent? Now, there is some literature about if you can find out what people are planning to do, well, that's like spying, right? So you can do this in industrial espionage or war espionage. Of course, that's often useful. I mean, that's always useful if you can really find out what they will do. But I am thinking about more, is it important to understand the motives of the opponent completely? So for instance, it's possible that there are some spots about where people prefer to race, and the spots where you don't like to race. Maybe there are some flights that would be easier for terrorists to attack. Maybe that's where they live. So there are things that maybe should you think deeply about this. So in my example here, it will be something like, what if your opponent might have a preferred side of some kind? Maybe they jump more easily to the left or more easily to the right. Is this something that you really want to know? Do you want to think about this deeply? Do you want to investigate this? Do you want to have this deep sort of cognitive empathy? And I want to insist on the term cognitive empathy. So I don't know, when you hear empathy, usually you think about, oh my God, you poor guy, or something like this, right? Sort of this deep affectional empathy. But there are two parts of empathy, right? And maybe you're a psychologist, some of you, so then you probably know this distinction. But so affective empathy is that you cry with others if they cry, you laugh with others if you laugh. But cognitive empathy is just that you put yourself in the shoes of the other person without any moral an emotional attachment. Okay, and the cognitive empathy part is, of course, an important part to have the second kind of empathy. If you don't have the first, you cannot really have appropriate affective empathy. But in conflict situations, you're probably not gonna cry with the other people. Okay. Anyway, so it's about cognitive empathy, or some people call it theory of mind. So I want to basically explain to you today, and you will see my result would be that in such situations, theory would suggest this sort of I think appropriate theory would suggest that in conflict situations, you will only expect partial cognitive empathy. You don't expect people to have full cognitive empathy. And because it's not needed, it turns out, of some kind. So we will see how this goes. I don't want to go into this. I just want to tell you that, of course, there is literature. I'm not alone in this world to study things like this. This is all sort of close in some way or another. I just want to have this here so that you know that people, that I'm not doing this in a vacuum in some sense, okay? But I want to study this with game theoretic tools. That means I want to understand, something I want to develop a theory of cognitive empathy. And it's about interaction, as I said. So now I want to use game theory. So what does game theory need to be useful? So when you write down a game, it's a mathematical object. What you need to have? You need to have a few things. You need to have players. These are the people that make decisions in your situation. So you need to have, and you need to, of course, think about deeply what you want to put into this, okay? In our conflict situations, it would be fairly easy. You have one side, I mean, if you look at the goalkeeper case, you have the goalkeeper, or the penalty case, goalkeeper and kicker, okay? It's quite easy. But sometimes you may want to add the referee as a player. Sometimes you may, and if you have more complex situations, it may involve many, many, many more individuals, okay? But I want to keep that easy today. Then you have to think about what can they do in principle. Now, this is not something, should not be guided by what you see them do, because you want to explain what you see them do. You want to think about what could they do, and then you want to say, of all the things they could do, I'm going to tell you why they do what they do. Okay? This is what game theory could be useful for. So it's the possible things you could do. I mean, for instance, I always do this when I teach my first year introduction to economics. I think a nice thing to think about is when you go from A to B, you have a million ways to do this. You can go from here to another place in Graz via Vienna, but you don't do this, okay? And we understand completely why you don't do this, because it would take a long time. And we understand what your goal is. Your goal is to do this very quickly, okay? Most of the time. And so we can predict. So this is very much the same thing. So we have these people, we have what they can do, and then we have the information that they have. This is important because not everybody knows everything, okay? So it's important to understand sometimes what people know. And in fact, I'm going to have a very important information structure. I want to make people not know initially what the opponent is like exactly, but then they can learn it if they want to. This is what they have empathy. They can do, with some effort, they can have sort of this cognitive empathy and put themselves into the other person's shoes. But yeah, and I want to start think about what information people will want to acquire. And finally, you want to have payoffs. That means, so what does this mean? This means how these people like these various possible outcomes. So for every possible thing that can happen, for every possible strategy choice of all these players, you want to say, okay, and how do you like this now, okay? In fact, this is what I understand if you give game theory advice to companies, usually writing it down as a game and asking these questions is already the most important step. Who are the important people in your business, okay? What can they do, and will they want to do this, okay? So this is sort of important. And finally, so this is the game. This is when I have this done mathematically, I will describe all these things as mathematical objects. Then this is what is called the game. And then for a game, I need to have what's called a solution concept. It's not a great term, but it's basically a mapping that people have in some sense agreed on. We can talk about, there are many, many solutions, but I'll use the very basic one that you'll see. But it's basically a mapping for every game, it tells you what you think can happen in such games. So once you put in all these things, it spits out what the prediction for this game. Now, actually, there are some computer programs that can do this for you to some extent, but they're very limited because finding Nash equilibrium, which is the solution concept that most people use, which has good reasons, so this is not something that is easy to compute in general, okay? So usually this is a little bit like the art of the game theorists to identify these a little bit, and you have to find clever ways of doing that. But this is what a game would be like, and I'm going to tell you how I would apply this to the question of cognitive empathy in penalty kicks, okay? Which may be a little bit, and I make it very simple as an example, okay? Okay, unless you have questions at some point. So I'm interested in this idea of penalty kicks, at this moment, but this is a much more general. So when I go to this next slide, then the model, it will be much more general, okay? But so let's say we have this following game. We have two individuals, a goalkeeper and a kicker. And what can they do? I'm highly simplifying, okay? In fact, the Palacios Huerta paper, but only adds to another middle option. So here I'm only allowing these people to either kick and jump to the left or right. It's a simplification, okay? But we just want to understand sort of the basic, we want to understand some of the basic ideas. We don't need, we can add more actions later. Of course, there are interesting options if you understand penalty kicks. There's the panenka, there are other things that you could add that, okay? But it wouldn't change dramatically the insight of this, of what I'm going to give you. In fact, the general model would be much more flexible. So these are, we already have two things. We already have the players and we have their actions, their strategies. Well, they're actions in some sense. We don't have quite the strategies, we'll see. So we have this goalkeeper, and I'm going to denote them as blue, and the kicker will be red. And we have now payoffs. We have to specify payoffs. And I'm not going to, this is going to take a while. This is a big matrix, okay, of things. But I will talk you through it. So what I want to have here is I want to work towards the paper that I will present to you, basically this idea of cognitive empathy question. And so I want to have different types of goalkeepers and different types of kickers. So we have two possible types, two possible identities of a goalkeeper, and they are here. So the first one only cares about saving the goal, okay? So what does this mean? This is, so L and R are what, I can use this perhaps, right? Yeah, L and R are left and right. This is where the goalkeeper can jump. Okay, so this is from the goalkeeper's perspective. And L and R, the red ones, are where the kicker can kick. And this is hugely simplified in reality, but never mind. So if the goalkeeper jumps left and the kicker kicks to the left, the idea is you save, okay, because you're in the right place. And that's great for you. You as the goalkeeper, you win. Okay, in some sense, you save the goal. Okay, if you jump left and the other person kicks to the right, it's a goal and you lose. As simple as that. Okay. Now, of course, in reality, you might want to add probabilities to these things. This is not quite like that. In reality, there's always the probability that even if you kick left and the goalkeeper jumps left, that they will not get it. There's also a probability that you miss many things. Okay, but you know, this is a simplification that I think you can understand. So this is the normal, a normal goalkeeper will have preferences probably like this. They either jump to the left or to the right, and it's equally good. All they care about is, will they save the ball or not? And this is given by this payoff matrix for the goalkeeper. At the same time, the ordinary kicker will probably have exactly opposing preferences, right? Let me go back to this side. So if you look at the kicker chooses now to kick left or right, and the goalkeeper chooses between left and right as well. And now if the goalkeeper jumps left and you kick left, great. Not great, sorry, -1, bad, okay? You didn't score a goal, okay? And however, you would prefer to kick to the right when the goalkeeper jumps to the left. This is, by the way, often called the matching pennies example of game theory. So this would be a possible goalkeeper and a possible kicker that could play against each other, okay? And maybe you already know what they should do. What would be the right thing to do for people like that? If this describes the world, if there's only goalkeepers like this and only kickers like that, how should they behave? Well, definitely they should be unpredictable. So in some sense, what they should do is they should behave as if they flip a coin to decide which way they go. They don't want to make this predictable. They don't want to say, there's no kicker in the world out there that is famous for always kicking penalties to the left. Because you would be stupid to do that, because then if you become famous for that, then the goalkeepers will know where to jump, and, well, they will jump there, okay? And then you will not score very often. So, and if you test this with professional soccer players, they do exactly that. They play more or less 50-50, unpredictably. I mean, so it's a bit more complicated because of the chances that I told you about, but it's more or less like that. So, and that's actually what I wrote down here. I wrote down, if you are the goalkeeper and you play against this kicker and you know it, then you want to randomize 50-50. If you are the kicker and you play against this goalkeeper, you want to randomize 50-50. Okay, this would be what you would do. However, I'm going to make this a little bit more complicated. I don't know how often this is relevant here. In professional football, I'm sure probably not. But one can still imagine it, and I think it's insightful, a little bit, helpful. So you can imagine that there is a different kind of potential goalkeeper. So everything is the same, except here you get a 3. How could we maybe justify this? It could be that this goalkeeper, to his teammates, bragged that I know where the guy's going to kick, and I'm going to jump left. Okay, so I know he's going to kick left, and I'm going to jump left. And he's bragged in some sense, or made a bet even. Okay, so put basically more effort on this. So this means that the goalkeeper would prefer this to happen. Would like to jump left, and the other guy to kick left. Okay, this is okay if you brag, but the question is, if the opponent knows that you did that, this might change how your opponent plays against you. So this is what we will talk about, okay? So this is one. So in fact, I have already these probabilities here. If you brag like this, and then everybody understands it means that you're getting a better payoff here. You're getting 3 now because of this additional accolade, this fame that you get from being right about your prediction or whatever. If your opponent understands that, then the opponent has to play this against you. They will not play left so much. They still have to play left. They cannot just play right, because if you then think, okay, I made this announcement that this is my payoff, everybody knows it now, okay, damn it, okay, but never the man. If now the opponent always in such cases would play right, well, then you would jump right. But still, this is better than -1, right? So it can't be that the opponent, again, you still have to be unpredictable, but you have to tailor the probabilities to these preferences. And what's very interesting in these conflict situations is that how you randomize here as the kicker only depends on this matrix, which is the goalkeeper's matrix, not on the kicker's. It's irrelevant. Okay, so this is a bit counterintuitive, but you really have to understand basically the preferences of your opponent to make the opponent what's called indifferent, so that the opponent says, okay, I can go left or I can go right. It gives me the same payoff. So let me check that this is true. This is exactly how you would calculate this. So why is left and right now for the goalkeeper equally good if this is how you randomize? Well, if you play left, you get a payoff of 3, probably 1/3, and a payoff of -1, probably 2/3. So that's 3 times 1/3, that's 1, minus 2/3, that's 1/3. Okay, so you get an expected payoff of 1/3. If you play right, you get an expected payoff of -1 times 1/3, plus 1 times 2/3, minus 1/3 plus 2/3 is again 1/3. So you're exactly indifferent. This is the only, so you need to be indifferent. Why do you need to be indifferent? Otherwise you would play one of these things fully. So, and that cannot be an equilibrium ever. So this is why you have this to, this is the key thing about these conflict situations, that in equilibrium, which is the solution concept I'm using, this Nash equilibrium idea, which at least in some cases can be tested, and for football goalkeepers, for penalty kickers, I think it's not a bad model. You have to randomize in such a way to make the opponent different, which means you have to base your randomization only on the opponent's preferences. So that seems to suggest that if you think about these conflict situations more generally, that you need to think deeply about, when you're protecting yourself from terrorist attacks, what the terrorists exactly want. So, I mean, you know that they mostly want to do an attack, okay, but maybe they have a preference. Maybe they would like to have a bigger place rather than a smaller place. I mean, you know, do you want to think deeply? This suggests somehow you should think deeply about this. So I have at the same time also a different kind of kicker. So this kicker, let's say, would suffer in some sense if left happened, okay? Maybe this person, somebody else made this brag that this is going to happen, and you said no, and so, okay, then that you would suffer in this case. Okay, so that means that, so here I change this number. Again, if the goalkeeper now knows that this is your matrix, the goalkeeper has to adapt the randomization. Before it was 50-50, now you have to put more weight on this action, okay, and less on this one, interestingly. Oh, did I get this the wrong way around? No, I think it's, so it's -4/5 plus 1, that's 1/5, 1, I think I did this wrong, didn't I? This is just for you to check, whether you understood. So if this person plays left, you get minus 4/5 plus 3/5. So that's how you should do it, right? Left gives you, with probability 2/5 gives you minus 2. That's minus 4/5 plus 1/5. So that plus 3/5, that means it gives you minus 1/5. And if you do it like this, you have minus plus 2/5 and minus 3/5. Yeah, it's minus 1/5. So it's okay. Again, you're indifferent. I mean, this is not really hard math, but this is a bit tedious. Okay. Okay, but the important thing is that what you should do. So if you had these meetings, okay, and you know that these two people are playing, etc., and they fully know this is what happens, then they should randomize 50-50. That's the equilibrium. If, however, this person meets that person, this person has to randomize 2/5, 3/5, and this person has to randomize 50-50. Okay, and if you meet this one with this person has to randomize 50-50, and this person has to randomize 1/3, 2/3. They have to adapt it always to the opponent's type. This is the key thing. Okay. So, but what I now want to show you, I mean, I will sketch this a little bit. I'm going to make this much, much more general. Okay, this is what game theorists often do. They don't want to just do this with an example. You want to say, okay, what is the class of situations where the result will be true? And then I will show you the following, that even all the stuff I just said to you, it turns out that if you have the smallest cost of learning the opponent's type, you will not want to learn it fully. That means you don't need, it seems, to learn exactly your opponent's type to do this in some sense. Which, it seems a bit surprising to me. It was surprising to me, but that's what I live for, these little surprises. Anyway, so is this reasonably clear? Any questions about this? So now, how do game theorists do this? Let me see about time management. Okay, I think I'm doing okay. So I want to do this more generally. It's still a conflict game with just two people. I mean, this is still interesting enough, I feel. It would be more complicated, but one could probably do something when there's more people involved. So we have two players, a blue and a red player. And then we have a finite number of payoff types, like I just had. We had two different goalkeepers, right? We had two different kickers. Now I have a finite number of these potential types. By the way, when I do everything with finite, like I'd like to do, then the math of choice that I will need is linear algebra. But you can also model things with continuum of types and things. Then the math of choice would be analysis calculus, okay? Because then you can optimize, you can do derivatives and so on. It's a little bit a question of what is more useful in terms of getting to what you want. But so the mathematical toolkit, I studied math at the Technical University in Graz, actually, before I was gone for 20 years in the world somewhere and came back in the end as professor of microeconomics. But I find all the math I learned useful. So I can't remember any sort of math that I didn't find useful later on, actually. So I'm a great fan of learning math. But, okay. So what you also need to have you have to describe this information structure. The information structure is now here given in a simple form that there is a commonly known probability distribution over these types. Now, this is a bit annoying in game theory, and some people have argued that you have to challenge this sometimes, and some people do. But we have to close it informationally. We have to make it a well-defined object. And so we have to say something like, okay, exactly who knows what, and so we need to know more than that. So we need to say, not only do we, so with this structure, sorry, I'm rambling a bit. When I do this, when I say this is common knowledge, this probability distribution over types, it's common knowledge. It means that both players know this. It means that both players know that they know this. It means that both know that they know that they know, and all of this. And all of this is important. This is a bit annoying, okay? So there are examples in the literature of where it matters, where I say, okay, we know that we know, but we don't know that we know that we know, okay? And that's changing things, okay? So this matters, okay? I can even give you, maybe let me give you a quick example. It's a short tangent. This is one of my blog posts, in fact. So I noticed that in my family in England, my wife is from England, and when we visit her family, we're all in a big house together, and we had this problem. It's a complete tangent, okay? So change of gear, okay? But what we had this problem is that when dinner is ready, which is always at random times a little bit. Okay, it's not always ready at the same time. When dinner is ready, people, it used to be the old system that we used was that the person who was cooking tries to get people, tells people that they should come down, dinner is ready, okay? And then people go off and try and find people. But then you have a situation where this can happen easily, and it happened many times, where everybody knows that dinner is ready, but not everybody's down yet. And why are they not down yet? Because some people are off because, yes, they know that dinner is ready, but they're not sure whether the other person knows, okay? So grandma might be looking around to try and find grandpa because she doesn't know that grandpa already knows that dinner is ready. And it could even be that somebody comes back, grandpa comes back, actually it's at the dinner table and says, oh, we just sent grandma off to find you, and then he goes and finds her, okay? Because he knows that dinner is ready, she knows that dinner is ready, he knows that she knows, but she doesn't know that he knows that she knows, okay? And it makes a difference. He goes off and searches, okay? So it matters. Sorry, I get very excited about these things. Our solution was the dinner gong. Because if you're dinner gong, everybody hears it, except the deaf grandmother. But if you have this dinner gong, then in principle, if everybody hears it, then they all know. Then it's common knowledge. Everybody heard it, everybody knows that they heard it, everybody knows, and then you can all come down and have dinner. So this is very applicable research. Okay. Anyway, so we have this. We need to have this probability distribution. We need to specify actions. Again, I'm doing this finite. Again, if you have not finite, if you want to have an infinite, a continuum, then your math of choice will be more calculus. So my math of choice will be here more linear algebra. So these are the things you can do, right? So, I mean, we only had like kick left and right, but in penalties, you could also have middle, perhaps. Or if you have, where do you attack? You can go this way, over this path, under this tunnel. I don't know. There's so many options in these other conflicts, okay? And you have to finally specify how everybody of every type feels about the different outcomes. Okay, so this was the matrix I had, right? So you have just some general arbitrary utility functions that map for whatever action you take and whatever action the opponent takes, and as a function of what type you are, how you like it. This is your utility function. This is your index of happiness if this happens. Okay, this is a shortcut for how people behave, perhaps. And so this is what I want to add to this setup, is that these players can, before they engage in this interaction, independently and secretly, very importantly, invest a certain amount of, let's say, thinking cost, or whatever it is, or maybe it's more real cost, to learn the opponent's type. They can think, okay, I'm going to put myself in the shoes of the opponent. This is a bit difficult, because thinking is hard. But if I do that, then I know I will learn fully what my opponent's type is. And I'm okay easy. So here we can fully learn this type. Okay, so this is the timeline. You have a time where I'm making it a bit easier for myself, but the timing can't be alternated. But I do it in such a way that before you even know your own type, you do this thinking. Or you can think about, you want to invest in this empathy, in this cognitive empathy. It costs you something, a small amount. Once you did that or not, then your type realizes. It means you learn your own type. Who are you? Okay. And then you may, if you learned this, if you did that, you learn your opponent's type. Okay. If you didn't, then you don't learn your opponent's type. Then at the same time, or after this, you simultaneously all choose their actions. Like, I mean, penalty kicks, you might say there is a bit of sequentiality, but it turns out goalkeepers cannot really react to the kick. It's too quick. Okay. So it's basically they make simultaneous decisions. Okay. And then payoffs realize, so something happens, and you get your payoffs. This is the timeline now. And so what are the strategies here? So the strategy of a player is now such that you have two components. The first thing is your information strategy. How much do you want to buy empathy or not? This is here, it's like in some sense, do you want to have it or not? You have to invest this amount C. So, and here what I want to allow you is I want to allow that people randomize over buying empathy or not. This randomization, we can come back to later how we can interpret this. But in principle, you could either say, I don't buy it at all, I buy it fully, or maybe I buy it with some probability. Okay, the opponent does not observe what you did. This is important. If the opponent observes things, then it's different again. Okay, so, and then there's this action strategy. So for every possible type that you could be, you have to tell me what you will do, what action distribution, will you play left? Will you play right? Will you mix? What you need to tell me what you will do. And not only as so, and now, but this is a function of two things. So it's a function of your opponent type. If you learned your opponent type, if you know your opponent type, then you can condition on that, right? You can say, well, but against this type I do that, against this type I do that. Or you didn't learn. That means I have this empty sort of signal here. That's supposed to mean you did not learn the opponent's type. That means, well, you still have to do something, right? Only you cannot make it specific for your type, for the opponent. You cannot make, so now if you don't learn the opponent's type, then there's just one standard action distribution that you have to choose. Okay? Oops. So this is the strategy space now for us. And we already have everything. We have our information structure, we have our players, we have our strategies, and we have our payoffs. Okay, everything is a bit abstract, okay, but it's all there. Now, I'm gonna make one assumption. I don't wanna talk about all kinds of games. So far, it's basically all kinds of games, right? So I wanna make this a bit more special. I wanna make it conflict games. I can say a few things about other games, but the conflict games is what interested me and is where I get this interesting result. So I call such what's called a Bayesian game sometimes. So this is called a Bayesian game. Why? Because we have this probability distribution over types, and whenever you get some signals, you update with Bayes' law. It's in honor of this guy Bayes from the 17th century, I guess. It's a long time ago anyway. I forget, Reverend Bayes, right? Who invented this updating. Or Bayes' law. So this is called Bayesian game, or game of incomplete information is also sometimes called. And I call it a conflict game if it is true what we had before in the example. If any realized type game, meaning if you take one type of one player and another type of another player, and they now fully understood what the game is, that this game has only one equilibrium. This is called a unique Nash equilibrium. And this is in completely mixed strategies, like we had in this football case, okay? We had this one equilibrium. So again, if the first two, maybe if I go back. So here, in this case, for example, if this is the game played, if this type realizes and this type realized, then this has a unique Nash equilibrium, both of them randomized 50-50. But no matter how the types realize, if they know it, there's always an equilibrium in completely mixed strategies, meaning that you always have to fully randomize. And this is the class of games I want to look at, because this is the class of games for which the result is kind of cool. So, maybe let me try and tell you this. So there's a small chance, I mean, I know this is all a bit steep in some sense, but there's a small chance that I can make this understood for you. So this can be, I think you might be able to understand this. Then the later result, I don't think I can fully prove it to you. I can try and convince you that it's true, but at least you will know what I'm stating. But let me first say this. And I think I can explain this a little bit. So for any conflict game, and for any positive cost of this empathy acquisition, okay, there is no Bayes-Nash equilibrium in which both players acquire empathy with probability 1. So it sounds complicated, I guess. But what does this mean? So suppose it was true that both players fully bought empathy, meaning they will always learn the opponent's type, whatever the type is, they will always learn it. Now what happened? If that happened, okay, suppose it were true. So it's like a proof by contradiction in some sense, okay? So suppose it were true that they all know each other's type fully because they learned it. Then they all know this as well. They know that they know that they know, and all that, okay? If this is the case, then they all know this. That means that if they now play a Nash equilibrium of this game, they always have to play this mixed equilibrium that I talked about in the beginning. 50-50, 2/3, 1/3, they have to do this exactly right, okay? Which means that if I go back to the penalty kicks game again, oops, too fast. This means that they play exactly with these frequencies against the right people, okay? But what does it mean also? It means that they're only prepared to do this. Remember, I tried to make this calculation based on the idea that you have to make the opponent indifferent. So it means that everybody is indifferent, really. You're only prepared to randomize because you know the opponent randomizes in such a way that you are completely indifferent between left and right. It doesn't matter to you. This is the funny thing about this. Is a bit difficult to completely intuitively comprehend because it's a bit counterintuitive. But the opponent does this if You meet like this. If you play equilibrium, the opponent randomizes in such a way that you are indifferent between this. And then you might also randomize. You don't prefer L over R, you don't prefer R over L, you're indifferent. But if this is now true, that no matter who you're going to meet, you're always indifferent between L and R, then you don't seem to know, then it sounds like you don't need to, for you personally, it makes no sense to know who you're meeting. Everybody against you will play so that you are indifferent. Well, then you can do whatever you want. You play L or you play R, you will randomize whatever you want. You don't need to know who you're meeting. So you're not gonna, that means that you will not want to learn empathy. So it cannot be an equilibrium. Equilibrium means that if the opponent really does this, then you don't want to do it, then it's not an equilibrium, okay? So I don't know, I haven't, of course, given you a full formal definition of what Nash equilibrium is, so I'm doing a few leaps of faith here. But this is the idea. Maybe equilibrium, maybe let me give you one quick other short story before we maybe slowly wrap up. So equilibrium is always tricky to understand a little bit, but let me give you an example of where you might understand what equilibrium means. So equilibrium is always a situation where, given what the opponent does, you do the best thing you can do, and vice versa. That's what an equilibrium would be. Now, let me tell you what's not an equilibrium. So I don't know, you may know in sports, there are some more strategic games than others. So there's some games like a 100-meter dash, not very strategic, okay? You just run as fast as you can, right? I mean, that's really quite boring strategically, right? You just go boom, okay? And that's all you do. But there are games that are more strategic. And the one that I find fascinating when I watch the Olympics, there's this called Bahnverfolgung, what's it called in English? So it's like, it's called the sprint. It's actually it's a very nice name because it's a bicycle race, it's a track race, the track cycle sprint race. And what do they do? There's definitely one thing they don't do. They don't sprint. So what you have is I don't know how it was invented, but it's a long time ago, and I've tried to look up. They have often had rule changes, and I can tell you why. The way it works is this, okay? You have these two bicyclists in the track, and they start, and then there's this person who shoots, right? And then you expect them to race off. That's not what they do. Why not? Because if they try to bicycle as hard as possible, that's not a Nash equilibrium. It means that if the other person bicycles as hard as they can, it's not in your best interest to do the same. Maybe you know about cycling, I don't know. But what is the best thing you can do in this case? What do you think? I don't know. Exactly. Yeah, you stay behind the other person, you go the 3 or 4 rounds, and then at the end you go, haha, and you go past them, okay? Because you're in the slipstream, you're faster, you have more strength, you save more strength, and that's what you do. And because this is not an equilibrium, this is not what happens, okay? And this is very much like that here. What I just showed you with this full empathy acquisition is not an equilibrium because if the other person does it, you don't want to do it. Because then, in my case, it's a bit more subtle, okay? But in this case, if the other person does it, you know the other person is going to make you indifferent no matter what, in which case, you don't need to know, okay? So it turns out in the bicycling, the thing is that what seems to be the equilibrium is that you start very slowly. Then people are trying to go back. They change the rules. They can't go back. People will say we're stepping down the foot. They change the rules because they didn't like that. So they had to make lots of rule changes because the equilibrium didn't turn out to be what they had in mind. I feel a little bit like at the moment Formula 1 Grand Prix racing is well, maybe it's better now again. I stopped following, but it became very boring at some point. Games become boring when it becomes clear what the Nash equilibrium is, in my opinion. Okay, then everybody knows how to behave. It becomes boring. And Formula 1 Grand Prix racing for a while was only about who has the better tire strategy, which is not the most exciting thing. It's not why you watch car racing, as far as I understand. Anyway, okay, so I will now only tell you really now the main result. Okay, so this is not the main result, but it's sort of already indicative that we don't necessarily acquire empathy with full probability. But it could mean that as costs are very small, the probability of acquiring empathy could be getting closer and closer to 1, right? That it could be the case. But it turns out that's not the case. So let me tell you what the main result is, maybe without this, and then we can discuss more. I think it may be more fun. So this is the main result, and I can state it completely formally, right? So, but maybe I should explain it in words. So give me any Bayesian conflict game, and now consider any cost of empathy acquisition. And for each cost level, I denote here rho CP. This is now the probability of empathy acquisition in some Bayes-Nash equilibrium of this Bayes and conflict game. So I'm looking at all possible Bayes-Nash equilibria of this game, of all of these kinds of games, okay? I'm able, luckily one can do this. And what I know is, if you take the cost slowly to 0, then the empathy cost will be bounded away from 0. You will definitely have to have empathy. So people will definitely have to buy empathy with some positive probability. I mean, also that's very intuitive, right? If nobody does, if you know your opponent doesn't know about you at all, then it's quite useful for you to know who he is or she is, and then do the appropriate thing. Okay, so that's quite, because they might do different things. So, okay, it's a bit more complicated, but it's sort of intuitive that you want to know a little bit. But the more interesting thing is that so if you take the cost to 0, then the empathy acquisition probability is also bounded from above. It's not that it gets closer and closer one, it's bounded. There's a definite gap. So only with some probability you will buy empathy, okay? I mean, so this can be made more, this is very formal, I guess. So here there are some exact numbers. I can actually quantify exactly as a function of some of the parameters of the game how this works, but this is not so interesting. I think the interesting thing is that you don't have 0 and you don't have 1. It's very clearly somewhere in the middle. Let me tell you how I interpret this. And this is how it would be proving this a little bit, but I don't think I want to do that. So what I want to say is that I can use game theory to study the theory of empathy acquisition, okay? I mean, you might say, well, this is just one way of doing it. Maybe it's just one way. But I think it's a fruitful way of doing this potentially. And so my game theory analysis suggests that in such conflict situations, I would only expect partial cognitive empathy in equilibrium, meaning, so I like this interpretation of randomization. If you think of a world of people out there, a world of goalkeepers, a world of kickers, okay, then you will find that some of them have empathy, this cognitive empathy, and some do not. And they don't suffer for it, at least not in these conflict situations, okay? So in these conflict situations, you have to have each of these, but those that don't have empathy don't really suffer for it, because the environment is such that they also get the same payoff in some sense. So all this is true, even if the cost of getting empathy is negligible. It can be essentially 0. That actually means, I mean, one could give as an example also a coordination problem. And actually there you want to have cognitive empathy in equilibrium. So in conflict situations, we expect less cognitive empathy than in situations with coordination concerns. And I don't know, you wanted to have a bit of time for discussion, I guess, so this would be a good time to leave a bit of time for discussion. So this is what I wanted to say. I don't know whether I managed to convince you completely, but I didn't prove this to you completely, right? But you have to sort of trust me. You can read the paper and go through it. But I wanted to show you how one can utilize this kind of game theory toolkit for questions that, maybe you wouldn't immediately think that this is something you could study with game theory. Okay, thank you very much.